Okay, hello everybody. I'm Alex May, and I'm based at Perimeter Institute. I'm going to be speaking about rank lower bounds on non-local quantum computation. And this is based on some joint work with my two collaborators, Vahid Asadi and Eric Kulf, who are both based at IQC. So let me start with some background and motivation. The main technical subject that we're going to be interested in is something called non-local quantum computation. So here, to explain this, let me start with this picture on the left. The setting is that we have two quantum systems, which I've labeled A and B. So those are sort of, you can think of as collections of qubits. And those systems initially start out separated. They're far apart from one another, but they're going to be brought together and interacted in some way, and then brought apart again. Okay, and we'll call that a local interaction. The goal of a non-local quantum computation is to reproduce the transformation that happens in that local interaction without ever actually bringing the systems A and B together in the same location. Okay. So the way that we're going to imagine doing this is illustrated on the right. So again, I have my system A and B, and what we're going to do is share some entanglement, some entangled state, this one here, psi, between the left and the right. And then we're going to act on the left with this operation VL on A and the portion of the entangled state on the left, and then on B and the portion of the entangled state on the right. Then there's going to be a round of communication. So some system can be sent from the left to the right, and then another one from the right to the left. Then another round of operations happens locally. The second round operations, WL and WR. And then at the end of the day, the overall transformation that enacts should reproduce at least approximately the one on the left, the local interaction. It turns out that all quantum operations can be realized in this non-local form. And the kind of question that we want to ask here is how much of different resources do we need in order to enact that transformation, in order to compute something non-locally? We are especially interested, for our purposes, in how much entanglement you need to share between the left and the right to reproduce a given interaction. So why are we interested in non-local quantum computation? Well, it turns out that there's many applications of this subject, and it's connected to many different areas. So for us, two of the most relevant ones are first, what's called quantum position verification. That's a subject in cryptography that I'm going to describe in a moment. And then there's another connection to a different subject in classical cryptography, which is within information theoretic cryptography. Okay, let me continue by describing in a little more detail the relationship to quantum position verification and in fact, what quantum position verification is. So in position verification, we have two players, a verifier and a prover. And what the verifier is doing is trying to determine the location in space, like the physical space-time location of the prover. Okay. The way that they're going to do this is the verifier is going to have two agents that are cooperating to try and check this position. And I've called those V1 and V2. And what those two agents are going to do is prepare some sort of inputs, could be classical or quantum systems. They're going to send them towards where the prover claims that they are. The prover then, if they're being honest, should take those inputs, perform some sort of computation on them, and then send the outputs back to the two verifiers, V1 and V2. On the other hand, if the prover is being dishonest, they're going to try and simulate the actions of an honest prover who would be sitting in the middle here by using one of these non-local quantum computations. Okay, in particular, the prover is going to have themselves two agents, P1 and P2, who are sitting on either side of the location where they're claiming to be. They're going to, in general, distribute entanglement across, well, between themselves. And then they're going to intercept these inputs from the verifiers, run some, perform some operations, perhaps using their entanglement, use this one round of communication, perform another round of operations, and then try to send back the correct response or the correct output to this computation. So what's important here is that the most general cheating strategy in a quantum position verification scheme is a non-local quantum computation. And that's in part why we want to understand how hard it is to implement those computations. Okay, so for the purposes of position verification, we're interested in schemes that are easy for the honest player to implement. So in particular, something that's easy to compute in the local form, but hard for the dishonest player to implement. So something that's hard, maybe uses lots of entanglement to implement in this non-local form. So one proposal that's been around for a long time and has some nice properties is what's called F routing. So this is specified by its inputs and outputs. So let me describe those. So on the left here, we have one verifier input, a string x of length n, and then also a quantum system, Q, which could be just order 1 size, small, let's say a single qubit. And then on the right, the other verifier inputs a second string of length n that I'll call y. Then what is the prover supposed to respond with? What is the correct outputs? Well, they should bring the quantum system Q to the left if some Boolean function of the inputs is 0. And they should bring Q to the right if that function is 1. So an honest prover would, in particular, bring x and y and q into the middle, compute f, and then sort of route or redirect q left or right, depending on the output of their computation. Okay, so why are we interested in this one in particular? Why is this relevant for position verification? Well, one thing that's nice is that the honest prover, like I was just describing, their operations are almost just classical, right? So they compute this function f of x, y, and then they do order 1 quantum operations to redirect the quantum system. On the other hand, it's been hoped and I think expected that a dishonest prover, somebody who's trying to implement the same transformation in the non-local form, needs lots of entanglement, and in particular, entanglement that grows with the classical input size n. Okay, so what are our results? We give the first non-trivial lower bound on entanglement cost in F routing. And by non-trivial here, I mean that the lower bound grows with the classical input size n. Okay. Now, there's a bit of a caveat there in that our lower bound only applies when we have some sort of perfect correctness. Okay, so we're going to consider protocols where we're either perfectly correct on 0 instances, which means that when f is 0, we bring q to the left perfectly, undisturbed, or cases where it's perfectly correct on 1 instances, which means that when f is 1, we bring q to the right perfectly. Okay, so to characterize those two cases, I have these two different measures of entanglement cost, which are indexed by this subscript b, which can be either 0 or 1, depending on whether I'm talking about perfect correctness for 0 cases or 1 cases. And what this thing is the log of the minimal Schmidt rank of any shared entanglement state, entangled state that suffices to implement the F routing task with the appropriate form of perfect correctness. So that's our measure of entanglement costs. What do we then prove? Well, we show that these are bounded in terms of something called the non-deterministic rank. Okay. So what is non-deterministic rank? How we define that is we think of this function f. We view it as a 2 to the n by 2 to the n matrix. So the rows are labeled by x, say, and the columns are labeled by y. And then we think about the rank, not of f, but of any function that has the same zeros as f. Okay. We minimize over all such functions, and we take the value of that minimum, and that's the value of the non-deterministic rank. I should also say that for certain simple functions, natural functions like, say, equality, it's easy to give a bound or to fully compute the non-deterministic rank of the function. So it might feel like an unwieldy object, but often you can just write it down explicitly in terms of n. Okay, so that's our basic result. Now I want to try and give you something of an overview of our proof technique. To start out, let's consider a totally general non-quantum computation protocol, which we assume implements the F-routing task. In general, we can have this system Q be in whatever quantum state we would like, but it will suffice for us to take in particular Q to be in a maximally entangled state with some reference system Q bar. Okay, so that's what I've indicated with this line here. The first step we're going to make is to simplify or only look at a portion of this protocol, which will keep things easier for us. And in particular, we're going to ignore the second round operations. And then I'm going to label the systems that end up on the left as M and the systems that end up on the right as M prime. We will focus our attention on the density matrix on those systems, which I'll call rho. You can observe that because the first round operations, whatever I do here, or whatever I do here, depend on x and y, this density matrix rho on Q bar M prime in general depends on x and y. A very important observation, which has been made earlier in the literature, is that there is a particular sense in which this density matrix knows about the value of f of xy. In particular, what one can show is that when f is 0, because it has to be possible to act on M and recover the entanglement with Q bar, it must be the case that M is already maximally entangled with Q bar. Okay, so when f is 0, we have this entanglement. Similarly, when f is 1, because I need to be able to recover Q from the right, from M prime, now I need to have entanglement between Q bar and M prime. So you can think of that observation as saying that somehow all of the structure in this function f of xy is also recorded into this set of density matrices, rho of xy. Okay. And those density matrices are computed in this particular form, this non-local quantum computation form. And somehow what we want to show is that in order for the structure of this rho of xy to sort of be rich enough to express the function f, we're going to need to have lots of entanglement shared between Alice and Bob. Okay. It's not clear how to make that connection, but it turns out that somehow the right question to ask here, or the question to ask that elucidates how this structure in rho reflects the structure of f, is to ask how you would compute f of xy from the density matrix rho. One thing that you can do to compute this is to compute this other function that I call g, and we sometimes refer to as the structure function. Okay. So how is g defined? Well, it's defined like this. So we take the marginal of rho on Q bar M prime, and then we subtract from that a tensor product of its marginals on Q bar and M prime, take the square, and we take the trace, and that's giving you g. Okay, so why am I looking at this function? Well, what's important here is that g is 0 if and only if f is 0. Okay, so why is that the case? Well, it's easy to see that if g is 0, or g is 0 if and only if rho Q bar M prime has this tensor product form. And what that is telling you is that there is no entanglement between Q bar and M prime. And then in quantum mechanics, we know that the entanglement sort of has to be somewhere. And in particular, that's going to mean that it's between Q bar and M, which, on the last slide I was explaining means that f of xy is 0. Okay, so this function g, the structure function, is something I can compute from the density matrix that is 0 if and only if f is 0. So then to continue the proof, what we do is we take the form of rho that's given to us by this circuit picture with this shared entanglement that I drew before, and we just insert that into the definition of g. We plug through the computation and simplify things down as much as we can, and what you find when you do that is that the form of g is constrained by the form of that circuit that computes rho. Okay. And in particular, what you get is that G can be written like this. So it's a sum of product of terms, where the number of terms in the sum is controlled by how entangled that state is between Alice and Bob. And in particular, the sum runs up to R to the 4, where R is the Schmidt rank um, of, of the shared state held by Alice and Bob. Okay. And that's, it's not totally clear that it will come out that way from what I'm saying, but it's just some direct calculation. Okay. And then we're basically done. So what we have is that, G has this form, has only this many terms, and that G is 0 if and only if F is 0. And one thing that that means is that the non-deterministic rank of F is not larger than the non-deterministic rank of G, which is not larger than this R to the 4. Okay. And yeah, then that's the proof. We just take logarithms and we recall what our definition of FR0 here was. And we find that FR0 is lower bounded by the log of this non-deterministic rank of F. And the power of 4 up here means that I have the coefficient of 1/4 there. One comment that I want to make, that just to come back to something that I sort of skipped over in describing the proof, is that connection where I argued that G is 0 if and only if F is 0, if you want to make that precise, you're going to end up using perfect correctness on 0 instances. Next, what I want to describe is a relationship between this F routing setting and a primitive in information theoretic cryptography called conditional disclosure of secrets, and how this new technique for bounding F routing gives us a new technique for bounding CDS. So let me describe in detail what this CDS primitive is, or conditional disclosure of secrets. So this involves 3 players. There's Alice, Bob, and the referee. Alice gets an input X, which is a string of length n. Bob gets an input Y, which is a string of length n. Alice additionally holds some secret, which could just say be a order 1 size string. Alice and Bob can't talk, but they can share randomness, and they can each send a message to the referee. What they want is for the referee to be able to learn the secret if and only if some condition on their inputs is met. So we're going to consider that there's some Boolean function, f of xy, and when it's 0, we want the referee to not learn anything about the secret, but when it's 1, we want them to be able to recover the secret. Okay, so somehow Alice and Bob have to use their shared correlation to sort of coordinate their messages in such a way that the referee can learn the secret only when appropriate. Okay. So this was introduced by Gertner and others back in 2000 in the context of private information retrieval. It's since then found a number of applications, so in particular in attribute-based encryption, in the construction of secret sharing schemes, and in other places. To me, the thing that's most interesting about CDS is that it's just a very simple setting in which you can sort of understand the cost of privacy, or more generally, the sort of relationship between things like privacy and communication and shared randomness. This is really one of the simplest settings in which those kind of interplay. Another reason that it's interesting is that CDS is sort of the weakest among a family of primitives that are studied in information theoretic cryptography. So putting lower bounds on CDS also places lower bounds on a number of other settings. Okay. So it turns out that CDS is a sort of classical analog of F routing. And this was found in a recent paper with myself and collaborators. And for our purposes, 2 of the relevant things that we found there is that if I consider CDS with perfect privacy, so the referee should not be able to learn anything about the secret, beyond sort of randomly guessing, then the randomness cost of implementing that for some function f is lower bounded by the entanglement cost in F routing with perfect correctness on 0 instances. Okay. And then similarly, if I instead think about CDS with perfect correctness, okay, so now when F is 1, the referee recovers the secret, 100% of the time. Then that setting, the randomness cost, is lower bounded by the entanglement cost for F routing with perfect correctness in one instances. Okay. So because of this connection, and employing the lower bounds that we prove in this paper, we get a new technique for putting lower bounds on CDS. Okay. And in particular, we get this lower bound in terms of the log of the non-deterministic rank. So to compare these lower bounds to existing techniques, it's useful to relate the non-deterministic rank to something that's a little bit more familiar. So in particular, we're going to make use of a characterization from Ronald DeWolf, proved in the early 2000s, which showed that a particular communication complexity setting called the QNPCC complexity, quantum non-deterministic communication complexity, is characterized tightly by the log of the non-deterministic rank. One thing that means is that we can rephrase our lower bounds in terms of this communication complexity measure, and in particular, we can look at the perfectly private lower bound for perfectly private CDS, which is in terms of QNPCC. So to compare that to what's known, there's some lower bounds already from communication complexity on CDS and different variants of CDS. And these were proved by Applebaum and Vasudevan in 2021, or the ones that I'm mentioning were. And they showed in particular, or for instance, that perfectly correct CDS, the randomness as well as communication cost are lower bounded by co-NPCC complexity. And for perfectly private, they lower bound the communication cost in terms of the PPCC complexity of F. Okay. It's also known, or at least easy to show, that the perfectly private CDS is not lower bounded by NPCC. So this, what I'm showing here is false. Okay. So this was the status before our work. Looking at this lower bound on perfectly correct from this co-NPCC complexity, you might have guessed that perfectly private, would have an NPCC lower bound, but that turns out not to be true. And the bound that we do have from PPCC is, somehow quite weak. PP is a very large complexity class. Okay, so we, add to this story, and in a way that I think fits in kind of nicely, in that we show that while yes, there's no lower bound from NPCC, if you relax this a little bit to the quantum setting, you do get this lower bound. One final comment that I want to make about this is just that, thinking about this lower bound, and maybe it's clearer for this comment to think about it in terms of the non-deterministic rank, that lower bound is something that I can phrase in totally classical language, but nonetheless, there's no known proof sort of within classical information theory or classical cryptography of this bound. And instead, to find the proof, we had to go through this detour of thinking about quantum information and F routing and all these things. Okay, so in the interest of time, I'm going to say this very quickly, but I just want to add a comment here that this same technique that I'm describing can be applied to at least one other example of non-local quantum computation, one called FBB84. This is an example that is of interest in an experimental context, as something really feasible to implement for this quantum position verification setting. And we get a similar lower bound. Again, we need to deal with perfect correctness, which of course means that our bound is not really relevant for the experimental setting where it's going to be noisy. But we hope that our technique is some kind of a starting point, or our result is some sort of progress towards getting good bounds in this robust and experimentally relevant setting. Okay, so I'll just wrap up with a few final comments. So the main result here is that we find a new technique for proving entanglement bounds, entanglement lower bounds on non-local quantum computation. And in particular, our technique applies to F routing and to this other case, FBB84. This result is relevant to the security of quantum position verification. One byproduct of this is that we obtain a new lower bound technique for conditional disclosure of secrets. The bound that we get is on the new lower bound that we get is on the randomness cost for perfectly private CDS. And it's in terms of the QNPCC complexity. As I commented before, there's no known classical proof of this sort of a result. And so it seems to be some contribution from quantum information theory to classical information theory cryptography. And then finally, there's lots of open problems here, ranging from small ones to big ones. A bigger problem is, as I kept mentioning, to address the robust case. And I think that's a really important open problem, both for CDS and for QPV. And the way forward is not clear, but well, that's why I've listed it under big problems. Okay, that's everything. Thanks a lot.